You know, when you're sitting in an exam, have you ever wondered what the person marking your paper is really looking for? Well, today we're going to pull back the curtain. We're not just answering a GCSE question, we're going to crack it wide open using the official mark scheme. This is all about learning to think like an examiner so you can scoop up every last mark. Let's get into it. All right, so here's our setup. We've got a reversible reaction with copper sulfate. And the question hands us a bunch of numbers right from the get-go, a starting mass, a product mass, and even some energy data. Think of this as your toolkit. Everything we need for the first couple of questions is right here. Okay, here we go. Our first challenge, a 3-mark calculation. The goal is to figure out how much water we'd get if we used a bigger pile of the starting stuff. All the clues are in that info we just saw. So just take a moment. How would you start this? So let's see exactly how an examiner gives out the points. Mark number 1, you get it just for doing a simple subtraction to find the water in the original experiment. Easy, right? The second mark is for finding what I call the scaling factor, basically how much bigger our new reaction is. And the third mark comes from using that factor to get your final answer. And check this out, the mark scheme allows for a bit of rounding. As long as your answer is in that ballpark, you get the full 3 marks. Okay, time to switch gears. We're flipping the reaction around and starting with a different amount of stuff. But this time we're not focused on mass, we're focused on energy. The question is, how much energy gets transferred if we use 15 grams? And see, this is a classic exam move. The logic is the exact same as the last question. First, you find your scaling factor, new mass divided by old mass. Then, you multiply that scaling factor by the original energy. It just goes to show you always want to show your work and keep an eye on those significant figures. All right, enough of the calculations for a minute. Let's move on to the principles of equilibrium. We've got a whole new reaction here. 2 gases, one is brown, one is colorless, and they give us one absolutely critical piece of information. The forward reaction is exothermic. That means it gives off heat. Remember that, it's going to be important. So here's a textbook Le Chatelier's principal question. We know the forward reaction gives off heat. And now we're going to crank the temperature up. What's your gut feeling? What's the system going to do to try and balance things out? And the mark scheme says it shifts to the left. So why does it do that? Well, Le Chatelier's principle is all about the system fighting back against any change. If you heat it up, the system basically says, whoa, it's getting hot in here. And it favors the reaction that absorbs heat to cool itself down. In this case, that means going in reverse, to the left. Okay, now picture that same mix of brown and colorless gas, but it's trapped inside this sealed syringe. This picture is a big clue. It's setting us up to talk about the next thing we can change, pressure. So, someone pushes that piston in, the volume gets smaller, which means the pressure goes way up. How is our little equilibrium system going to react to being squeezed like that? And more importantly, what's it going to look like? And the correct answer is, the mixture is a lighter shade of brown. Here's the deal. When you increase the pressure, the system tries to relieve that pressure by taking up less space. It shifts to the side with fewer molecules of gas. In our equation, 2 brown molecules combine to make just 1 colorless molecule. So the reaction shifts right, and the brown color starts to fade. All right, let's look at one more gas equilibrium. This time, it's hydrogen iodide breaking down. Now, for this one, I want you to pay really close attention to the big numbers in front of the molecules, the stoichiometry. Here we go with pressure again. But this is a bit of a trick question. Look closely at that equation. Count them up. How many moles of gas are on the left side? And how many are on the right? The answer to that is the whole key. And the mark scheme shows this is a 2-part answer for 2 marks. First, you get a point for just saying there's no effect. But the second and most important point is for explaining why. You have 2 moles of gas on the left and 1 + 1, 2 moles on the right. Since both sides take up the same amount of space, increasing the pressure doesn't favor one side over the other, so nothing changes. This is a quick 1-mark question. We all know catalysts are supposed to speed up reactions, right? But what do they actually do to the position of equilibrium? Where does the reaction end up? Yep, you guessed it, no effect at all. A catalyst is like a shortcut that works equally well in both directions. It speeds up the forward reaction and the reverse reaction by the exact same amount. So you get to equilibrium much, much faster. But the final balance point, the position of equilibrium itself, doesn't change one bit. Okay, for our final example, we're moving out of gases and into a solution. And this one's kind of cool because we have a really clear color change from blue to yellow, which makes it super easy to see when the equilibrium shifts. So the mixture is green. That tells us we've got a bit of the blue stuff and a bit of the yellow stuff all mixed together. Our mission then is to figure out how we can nudge this reaction to the right to make it more yellow. What's our move? The correct answer is to add more hydrochloric acid. It's that Le Chatelier's principle again. If you add more of a reactant, in this case the hydrochloric acid, the system will try to use it up. To do that, it has to shift the equilibrium to the right, which means, you guessed it, making more of the yellow product. And here it is, the final question. And honestly, this one gets to the very core of the entire topic. It's testing if you really truly understand what dynamic equilibrium means. Why do the concentrations just stop changing?
And this slide shows the two magic phrases the examiner is desperate to see. First, you have to say that both the forward and reverse reactions are still happening. They haven't stopped. That's the dynamic part. But and here's the second key point. They are happening at the exact same rate. So for every new product molecule that's made, one is turning back into reactants. It looks like nothing is happening, but on a molecular level, there's a constant, perfectly balanced dance going on.
So let's just boil all that down, shall we? To ace these questions, you've got to be precise. For the math problems, it's all about finding that scaling factor. For the theory, you need to know how temperature, pressure, and concentration push and pull the reaction. And when it comes to definitions, know the exact keywords they're looking for. Look, understanding the chemistry is half the battle, for sure. But knowing exactly what the examiner wants to see on the page, that's how you turn a good grade into a great one. So the real question isn't just about what you've learned today, it's about how you're going to use this insider's look to completely change the way you revise and answer questions from now on.